Alright, hello everybody. My name is Alessia, and I am the lead lecturer here at Pearl Street Studio. Welcome to our introductory lecture on nuclear energy. So nuclear energy is one of the many energy resources that is used around the world for generating electricity. So the goal of this lecture is to help people understand what exactly nuclear energy is, how it is used to generate electricity, and discuss some of the considerations around using it as an energy resource. But before I dive in, I did want to mention that this is lecture 5 in our course, Introduction to the Electricity Industry. If you haven't already, we highly recommend that you go back and watch our lectures on coal, crude oil, natural gas, and geothermal, as this lecture references some of the material we went over in those lectures. If you haven't watched them, we will be adding a link in the notes to this YouTube video, so you can, or a link to these lectures, so you can find them there, but you can also visit our website at pearlstreetstudio.org to find the videos. All right, with that, let's dive in. So what is nuclear energy? Nuclear energy is the energy that is released when atoms are either split or bonded together, releasing energy in the form of thermal energy and radiation. And so the electricity industry utilizes the reaction where atoms are, one large atom is split into smaller atoms, and this is called nuclear fission. And so nuclear fission is the process of breaking apart a larger atom into smaller atoms, and in this process, it releases, yes, the smaller atoms, maybe some neutrons along with it, while also releasing that thermal energy and that gamma radiation. So if we look at this simple diagram I've done here, a little red dot represents a proton and a little purple dot represents a neutron. So in a fission reaction, we have a neutron that is fired at a very high speed at an unstable larger atom. And then when this happens, the unstable larger atom splits into two or more other atoms, maybe releases some neutrons along with it, and then releases thermal energy and gamma radiation. Now, before moving on to the next section, I did want to discuss gamma radiation a bit. So if you're not familiar with it or you don't remember it from when you learned it in chemistry or physics, gamma radiation is just a very high energy wave. It's the same kind of basic thing that visible light is or radio waves are, but it contains a lot more energy in it. And so gamma rays are given off during certain nuclear fission reactions, but we're going to discuss the exact fission reaction in just a moment, the one that's used in the electricity industry. But why I'm talking about gamma radiation specifically right now is that there are some big concerns around gamma radiation and how it can impact the human body. So these rays contain so much energy that they can actually penetrate through substances, such as the human body, and cause damage to living cells and DNA. And this is a pretty important note to keep in mind throughout this lecture on nuclear energy. Okay, so that's nuclear fission at a high level. But now let's take a look at nuclear fission to produce energy, specifically for the electricity industry. So here we have this same diagram, but now it's been labeled. So in the context of the electricity industry, when nuclear energy is harvested to generate electricity, the element that is typically used is uranium-235, but shorthand it's referred to as U-235. And so in this process, U-235 is hit with a neutron, and it splits into barium-144 and krypton-89, while also releasing 3 neutrons as well as the gamma radiation and the thermal energy. And so then what happens here in a nuclear power plant, you have this reaction, and this is the thermal heat that we want, like we have discussed in previous lectures. But how this is sustained is that these 3 neutrons that are released from this initial reaction then go on to potentially hit another unstable uranium or U-235 atom, which then has a chain reaction. It breaks up into other atoms, releasing more neutrons, and the reaction continues from there. So not all of these neutrons that are released will hit another uranium atom, but this is generally how the chain reaction happens. That provides a continuous source of thermal heat, and this is what's used in a nuclear power plant, which we're gonna cover in just a moment. Now, before we go into how a nuclear power plant actually generates electricity, I first want to dive into a little bit more about what exactly nuclear fuel is. So, as you've probably been able to pick up here, instead of burning fuel like coal or natural gas, nuclear power plants generate this thermal energy through nuclear fission, typically with U-235. And so, but one of the problems when finding U-235 in Earth's crust is that it typically only makes up 1% of the uranium that is found in Earth's crust. But in order to sustain this kind of chain reaction that I've described up here, the concentration of U-235 needs to be at about 3 to 5%. So what happens is when uranium is mined, which we're also going to cover in just a moment, after uranium is mined, it then has to go through a process called enrichment. And in the enrichment process, it increases the amount of uranium in a fuel substance to 3 to 5%, which is used in the nuclear reactors. And so then after the enrichment process, the uranium is then manufactured into these small pellets of uranium dioxide, which are then stacked here into these long metal rods called fuel rods. And then these fuel rods are grouped into what is called a fuel assembly, this is what is eventually placed and used in a nuclear power plant or a nuclear reactor. Okay, but before we go into how a nuclear power plant works, I do want to discuss how uranium is mined, because we've been talking about that. Where is it originally coming from in our previous lectures? So there are 3 main methods for mining uranium. There is in situ recovery, there is open pit mining, and then there is underground mining. So in situ recovery, it is a method of extracting uranium without digging a traditional mine like you saw in the coal lecture. So in this method, there are 2 wells that are drilled into an underground rock formation that contains uranium. So here you can see there are these 2 wells, and these little yellow dots here, let's zoom in a little bit, these little yellow dots, oh, nope, I gotta change my pen color, here we go. These little yellow dots here is uranium. And this in general here, this is ore with uranium in it. Okay. And so what happens in these wells, there is an injection well and a recovery well. So this is the injection well. And this is the recovery well. And so what happens here is that a chemical solution is then injected into the injection well. And this solution is then released at the bottom here when it's at this level of ore that contains uranium. And the solution dissolves the uranium as it flows through the rock. And the liquid containing the dissolved uranium is then pumped back up to the surface through this recovery well or production well. And at the surface, the uranium is then separated from this chemical solution and then processed into like a uranium concentrate. So one of the benefits of this mining method is that it leaves the region mostly undisturbed in comparison to other mining methods. And then the other mining method, which I briefly mentioned, is open pit mining. So open pit mining is very similar to what we see in open pit mining for coal. The process begins by removing soil and rock and other material that's above the ore that contains uranium, and then the excavators are brought in to dig up that ore, and then trucks pick up that ore and transport it to a processing facility where the uranium is extracted from the mined rocks or the ore. And then the third method is underground mining. Underground mining is simply just the process of digging mine shafts that go deep underground or into mountains, so that ore that contains uranium can be mined. And similar to open pit mining, trucks are then used to transport that ore and those rocks to a processing facility where the uranium is then extracted. Okay, great. Now, before we go into how a nuclear reactor works, there's one last thing that I wanted to cover. And that is, how does the energy density of nuclear power compare to other resources? So I've discussed when there's a nuclear fission reaction, it releases radiation, which can be pretty dangerous to human life, and there's a lot that uranium has to go through, a lot of processing so that it can be used. It can be prepped as a fuel to be built in a nuclear reactor. So that's a lot of effort. So it's like, why not just use coal or crude oil or natural gas? And the main reason is because of the energy density. So while refining and enriching uranium takes a lot of time and resources in comparison to coal mining, and then drilling and fracking for natural gas, uranium has a lot more energy in it than any of the fossil fuels. So in order to compare the energy densities, I took a look at the University of Calgary's energy education website to find the energy density comparison between different energy resources. And so here in this example, I'm not using units, I'm just using it as a general comparison. If coal is considered to have an energy density of 1, so it has X amount of energy for every kilogram or every pound of coal, gasoline, for the same weight, for like 1 kilo or 1 pound of gasoline, has about 2 times the amount of energy as coal. So it's about 2 times as energy dense. Same with natural gas. Natural gas is a little bit more energy dense than coal. But nuclear fuel is about 160,000 times more energy dense than coal, which is like insane. It's very hard to visualize. So in order to visualize this, I've actually drawn a little diagram. That is, I'm going to call it roughly. I'm going to call it roughly to scale. So if we compare, if we use the area of these squares as equivalent to the energy density of a fuel, if we go all the way down in this bottom corner, we can see this little red square represents coal, and the blue square represents the energy density of natural gas and gasoline. And then if we zoom out, this ginormous yellow square compares how much energy nuclear has in comparison to coal and natural gas. So I thought this was a fun visualization to add here. Okay, so we've gone through a lot of information about nuclear energy and nuclear fuel. Now it's time to dissect how a fission nuclear reactor works. So let's go here. So there are many different types of nuclear power plants, but in this course we are going to focus on the most common type of nuclear reactor, and it is called a light water reactor. And a light water reactor is the most common across the world. And there are actually 2 different types of light water reactors. They function pretty similarly, but they have one main nuance difference. And these are called boiling water reactors and pressurized water reactors. So in a boiling water reactor, here, we have this here, it generates electricity by using the thermal energy from the nuclear fission reaction to boil water directly inside of the nuclear reactor core. So let me label this diagram first. So this, you can see there's this, this structure here that is, there's this structure here, and this is called the containment structure. Let me zoom in a little bit more. Oops. containment structure here. And then this thing right here is called the reactor core. Reactor core. And then these gray rods here, this is the fuel assembly, which we talked about earlier. Fuel assembly. Did I spell assembly right? Nah, close enough. You guys get what I mean. That's the fuel assembly. So here, in a nuclear reactor, we have the fuel assembly, which contains all of that nuclear fuel. And there's this reactor core that contains these rods. So when a nuclear fission reaction is initiated, it's contained within this reactor core. And in a boiled water reactor, normal water, like the water you get out of a tap, is sent into the reactor core, and the heat that is released from these nuclear rods is then transferred to that water. That water is then boiled and it turns to steam. That steam is then used to turn a steam turbine, just like we've talked about in our other lectures. That steam turbine then is connected to a generator, which converts the kinetic rotational energy of that steam turbine into electricity, which is then transported by power lines to the electric grid, which is then distributes electricity to all of us consumers. And so then after the steam passes through the turbine, the steam is then cooled and condensed back into water, and then it is recycled through the reactor here to then be heated and boiled again and circle through this loop. Now the containment structure here, I briefly mentioned that before. The containment structure contains anything that is contaminated with radioactivity. And this is in the event, like, let's say something happens here. There's a leak somewhere along here, and nuclear waste spills. There's some sort of, like, radioactive contamination here. The containment structure is so that that radioactive contaminated water or equipment doesn't leak out and go into the water and soil that is around the nuclear reactor. So one of the things to note here with a boiled water reactor is that the steam here, the water in this loop is highly radioactive because it is touching these radioactive rods as the fission reaction is happening. And this also means that the steam turbine that is connected here also becomes radioactive because the steam is going through this turbine. So that's an important thing to note in a boiled water reactor system. Now the second type of system is a pressurized water reactor. And so a pressurized water reactor also generates electricity by using thermal energy from the nuclear fission reaction, but in this system it has two different water loops. And so here there is again, I have some writing left over here. This is the reactor core, I didn't have to write that. And then again, this is the fuel assembly. I think that's assembly, close enough. You guys get what I mean. So there's the fuel assembly there. And then this kind of turquoise water that I have here is the pressurized water. Oops. Pressurized water. And this is the loop. I'll just call it water loop 1. Let me move this here. Oops, water loop 1. Okay, so the reactor water, so this is the water that is touching these fuel rods in the fuel assembly. This reactor water is kept under very high pressure so that it doesn't boil. And if you remember back to our geothermal lecture, and you remember back to some of your intro chemistry, the higher the pressure a substance is under, the higher the boiling point is. So the water in this loop in this primary loop here, this first loop, can reach temperatures of above 300 degrees Celsius or above 572 degrees Fahrenheit without boiling, because it's under immense pressure. So in this first loop, this hot pressurized water flows through a heat exchanger. So it flows here. And so this thing here, this is a heat exchanger. Heat exchanger. Where what happens here is that the heat from this this high pressure water loop transfers its heat to a second isolated water loop. So the water that's in this secondary loop here never touches the water in this primary loop. The heat is transferred between pipes that go through the heat exchangers. So let's label this as water loop 2. Okay, and then the water in the secondary loop is typically at atmospheric pressure, and so it boils at 100 degrees Celsius or 212 degrees Fahrenheit. It boils into steam, which goes through a steam turbine, which is connected to a generator, which generates electricity, which then sends that electricity out to the electric grid, just like we've discussed before. Then this water, or the steam, once it's gone through the steam turbine, is then condensed back into water and then goes back through this loop. Now, because the radioactive water in the primary loop never touches the turbine system that's over here, the turbine hull or the turbine equipment remains free of contamination. So even though a pressurized water reactor is from a design standpoint a bit more complicated because it has these 2 loops instead of 1 loop, there's less equipment that is contaminated with the radioactivity in a pressurized water reactor. Okay, so that is how the 2 main types of nuclear power plants across the world work. In a future lecture for a different course, we'll go over some of the other designs of nuclear reactors, but this is good enough for an intro course. All right, so now let's go over some of the characteristics of a nuclear power plant. So nuclear power plants are dispatchable because operators are able to control the rate of the nuclear fission reaction. Now, to understand how that happens, it requires diving into some technical detail, but I'm not going to go over that now. That, again, will be something that will be reviewed in a future course. So, although operators can change the electricity output of a nuclear power plant, one of the common nuclear reactor types, a Westinghouse AP1000, typically takes a couple hours to change its output. So it doesn't react as fast as, let's say, some of the natural gas power plants. Okay, now looking at the fuel supply chain. So the fuel supply chain for uranium-235 for nuclear power plants begins with the mining of the uranium ore from the ground. So we start with this. And then once the uranium ore has been extracted, the uranium is then processed and enriched to increase the concentration of U-235. So it goes through the enrichment process. And then once it has been enriched, it is sent to a fabrication facility where it is manufactured into small ceramic fuel pellets like we had talked about. These pellets are then stacked into fuel rods and then grouped into fuel assemblies, which is what this little sketch is right here. And then these fuel assemblies are then transferred to the nuclear power plants. But because uranium fuel contains an extremely high amount of energy for its mass, relatively small quantities of fuel can power a nuclear reactor for many months or even years before refueling is required. So they can store a lot of fuel on site. And then the last step is the waste management. And the waste management I'm going to discuss in the next part here. But first I'm going to finish going through the fuel supply chain. So as mentioned before, there are, or did I mention this before? No, I guess I haven't mentioned it yet. There are a limited number of countries that have uranium resources. So if you're a country, for example, Kazakhstan, which mines a lot of uranium, Kazakhstan can send that to a port somewhere, and that the uranium can then be loaded onto a port, or loaded onto a ship at the port, shipped somewhere across the world, to an enrichment facility. Dropped off, and then it goes through the same process as mentioned before. Okay, so now on to fuel storage. So as I mentioned earlier, one of the advantages of nuclear power plants is that they can store several years worth of nuclear fuel on site because uranium fuel has an extremely high energy density. So only a very small amount of fuel is required to operate a reactor for an extended period of time. So at nuclear reactors, typically the nuclear power plants will refresh their fuel assemblies every 18 to 24 months. Now, this large on-site fuel inventory makes nuclear power plants more resilient to both short-term and long-term fuel supply chain disruptions in comparison to coal-fired power plants, crude oil product, and natural gas-based power plants. Now, there is the main concern here comes from the spent or used nuclear fuel. And this is the, after the fuel has undergone the fission reaction, it remains highly radioactive after it's been removed from the reactor. So although in this situation the fuel can no longer effectively be used to generate electricity, the fuel will continue to generate heat and emit radiation for many, many years. And so when a nuclear power plant is done with a fuel assembly, this spent fuel or used fuel is initially stored in water-filled cooling pools to remove the heat and provide a radiation shield. So that's what, didn't mean to delete my water, so I'm trying to circle here. There we go. It's stored in these pools, and then after a number of years in this pool, the radioactive waste is then transferred to what is called a cask, which is basically a huge cement cylinder for long-term storage. Now, the radioactive waste from these power plants remains hazardous for thousands of years, making the long-term management of nuclear waste and storage a very important engineering and policy challenge across the world. Now, I'm not going to dive into too many details here. This will be discussed more in the environmental and social impacts unit, which is Unit 4 in this course. Okay, on to the capital costs. So historically, nuclear power plants have required some of the highest capital investments and longest construction timelines of any electricity generation technology, often taking 10 to 20 years to design the power plants, to permit them, and to construct them. And the high capital cost from these power plants is the result of needing very, very extensive safety systems, very thick reinforcement concrete structures around these facilities, and very heavy regulatory oversight. Now, I took a look at the National Renewable Energy Laboratory's annual technology report from 2024. The National Renewable Energy Laboratory, also known as the National Lab of the Rockies, is a lab based at the United States. And in their report, they said that the cost of building out a nuclear power plant in the United States is about $7.8 million per megawatt. And the typical size of these power plants is about 1,000 megawatts. So if we look at the total cost, building out a new nuclear power plant is at about $7.8 billion, which is far more expensive than the other resources we have looked at. However, there are many companies and research organizations that are attempting to develop new reactor technologies that have the goal of reducing these construction costs. And if these technologies are successful, they could make nuclear power, building out nuclear power plants faster and less expensive, but that is still yet to see if that initiative is successful. Okay, on to operational costs. So although nuclear power plants they do require fuel like fossil fuel power plants, but the cost of the fuel is relatively low in comparison with the amount of electricity that can be generated from them. Because remember, your nuclear fuel has about 160,000 times the amount of energy as its equivalent weight in coal. So as a result of this, fuel costs make up only a very small portion of the nuclear power plant's operating expenses. The operating expenses typically come more from maintaining the nuclear reactor, maintaining the steam turbines, as well as other various plant safety equipment, and then also employing very highly trained staff and complying with rigorous safety and security requirements. There's also the incurred cost of needing to store very highly radioactive spent nuclear fuel, which if there is any issues with that, if there are leaks of this highly radioactive fuel, it can have very grave public health consequences if not dealt with properly. And the average cost about $33 per megawatt hour, which I have here. So the air pollution and greenhouse gas emissions. So because the electricity is being generated from heat released by nuclear fission rather than by combustion, nuclear power plants don't produce any air pollutants or any greenhouse gas emissions during their operations. So this makes nuclear power one of the lowest emissions energy resources. But as discussed earlier, the primary health concern and the primary waste product from nuclear power plants is that spent nuclear fuel, which remains highly radioactive even after it has been used. Okay, and then the last subsection here, the role on the electric grid. So nuclear power plants are primarily operated as baseload generation resources, and this is because that they are a bit slower to change how much electricity they're generating in comparison to some of the other resources. So they're typically operated at a constant, are outputting a constant amount of electricity throughout the day. So here you can see this is the same chart that I've shown in previous lectures. There on the x-axis is the time of day, y is the electricity either being demanded or generated. This blue line here represents the a rough pattern of electricity demand throughout the day, and then here you can see the nuclear power plant is just being operated constantly throughout the day. All right, and now on to our last section, which has a lot of information here. Our geopolitical considerations around, or the discussion of geopolitical considerations around using nuclear energy. So the first consideration, and probably the most concerning one, is the radioactive waste. So if radioactive waste does escape its containment, despite the many safety precautions that are made, there is a danger that comes through the radioactive material entering the water and the soil that's near the reactor site. So one of the byproducts from a fission reaction with U-235 is strontium-90. And strontium-90 is very chemically similar to calcium. So if somehow strontium-90 gets into the water supply, it gets into the soil, it gets into food, it can be taken up by our bones and our teeth and can cause bone cancer and leukemia. And because of its an element that exists for an extended period of time, contaminated land and water can remain hazardous for centuries. And once radioactive waste contaminates an aquifer, so underground water storage, it is extremely difficult and costly to recover this kind of system. So that's the primary concern. Another geopolitical concern is that there is a very low probability of a very, very destructive accident. So one of the major concerns is, the very small probability of extreme accidents. There have been 2 of these major accidents in world history. The first one was the Chernobyl disaster in Ukraine in 1986, and the Fukushima disaster in 2011 in Japan. And these events demonstrated that when there are reactor accidents, it can result in the release of radioactive materials that can have long-term environmental consequences, costly cleanup for the region, and health impacts on nearby communities. And even though modern nuclear power plants incorporate many, many layers of security, they have containment structures, they have strict regulatory oversight, etc. This does reduce the likelihood of such event, but because the potential consequences of an accident are so devastating, there are still valid concerns around the safety of using nuclear energy for electricity. All right, the third one is nuclear proliferation. And nuclear proliferation is the risk that the materials, the technologies, and or the expertise that is intended for building out electric power plants could be used to support the development of nuclear weapons. So for example, the uranium enrichment facilities that are used to produce fuel for nuclear reactors could be modified to produce uranium fuel at a much, much higher enrichment level, which could be used for nuclear weapons. Now, although most countries do operate their nuclear power programs under very, very strict regulations, and there's our international organizations such as the International Atomic Energy Agency that does monitor nuclear proliferation around the world, there are still concerns about nuclear proliferation in general. So here I've sketched out a map of the countries that are confirmed to have nuclear weapons. So that includes the United States, the United Kingdom, France, Russia, China, North Korea, India, and Pakistan currently. But there are some concerns that if more nuclear reactors are built throughout the world, there are worries that more and more countries will have access to nuclear weapons. All right, and then the last geopolitical consideration is the concentrated fuel supply chain of uranium. So Kazakhstan, as a singular country, supplies roughly 40% of the world's mined uranium, and this is according to the World Nuclear Association. The top 3 producers, which is Kazakhstan, Canada, and Namibia, account for roughly 75% of the global uranium mining. So if there's like a single mine that for some reason becomes unavailable, there's a political shift in any one of these countries, this could disrupt the entire market for uranium fuel. And here in this map, you can also see some of the other countries that also mine for uranium, such as Australia, we have China, we have Uzbekistan as well. And I think I have the annual, here, I also have the production in tons of uranium from each of these countries. So that's interesting to look at. Okay, cool. That is it for our nuclear lecture. Yeah. So this is the first version of our nuclear lecture, and we know that there is probably much to improve in this lecture, so we would love your feedback. Was there something that you think wasn't explained clearly enough? Do you think that there's other information that we should add here? If you have any opinions like this, we will add a feedback form. And then after receiving a sufficient amount of feedback, we will be updating the lecture, re-recording, and posting the updated video. So for those of you who provide feedback, thank you so much for helping to improve the quality of publicly available education. Also, if you found this lecture valuable, please consider donating to help us continue making publicly available educational content on the electricity industry. There will be a link in the notes, but you can also donate at our website at pearlstreetstudio.org. All right, well, that's it for this lecture. See you at the next one.